Well, let's kick it off. We've got a fun lesson today. It's all about recursion. I hear classes in the past have had some difficulty with this. It can be a pretty challenging concept, but I also know a few of you have already had some experience with recursion. A few of you have had used it actually in your challenges. So we will see how this class does overall with recursion. I don't think this is a real quote by Stephen Hawking. If it is, somebody can let me know, but it's basically to understand recursion, one must first understand recursion. And this is another quote that I found online. Not sure who it's by, but I thought it was a little elegant. It is through recursion that we can wrap our finite minds around the infinite. And with that, I would say some of the more abstract reasons for using recursion, you are solving through the reduction of complexity. Essentially, brevity is levity. And there is a higher cognitive complexity to recursion. So working through a recursive solution may not always be practical. There are definitely times when it is. But regardless, it strengthens your abstract and critical thinking. And it parallels proven mathematical theorems and repetition in nature in the sense that it is self-contained. And there is an elegance to that. Recursion is ultimately just another approach to problem solving. And all approaches have pros and cons. So it is important to consider, as it fits some problems better than another approach, like an imperative or iterative approach. And you may not necessarily know when it will come in handy or when the best time to use it would be. But you won't ever find out if you don't learn and understand recursion in the first place. There are three very simple rules to recursion. One, a recursive algorithm must call on itself. Two, recursive algorithms must have a base case, and this is the simplest solution. And three, a recursive algorithm must change its state towards the base case, because this is reduction of complexity. This may not be the most common approach to thinking about recursion, but I like to think of lists as very easy ways to remember a process. And if we could kind of extrapolate from proven methods like the scientific method, for example, right? We can maybe come up with a list of memorable steps in which to take to approach recursion. We'll go over this in more detail later, but to start, what you want to do first when you're facing an issue, when you want to utilize recursion, is you want to identify a starting point, and this would be identifying the base case. The base case is essentially the simplest case, the simplest solution that could be applied to your dilemma. And from here, you could start exploring additional cases. The more you explore, the more data that you collect, the more you have to compare. And by comparing this data, by relating harder cases to simpler cases, you can extract conclusions. You will generalize a pattern. You will find commonalities, and through these patterns, you can reach a final conclusion from which you can write out the code you need to execute. Before we dive into that in more detail, let's go over, let's say, the difference between a recursive solution and an iterative solution. So taking factorials as an example, if you remember factorials from your math class, factorials are when the product of an integer, n, and all non-negative integers below it are multiplied together. And this little image here shows that if we were trying to find the factorial of 4, we're really just multiplying 4 and every non-negative integer below it until we reach 0. So in an iterative or imperative approach, a solution may look like this. You're going to multiply n, whatever value you're given with n minus 1, and then n minus 2, and n minus 3, and so on and so forth, until you get to 1, which is your base case, which works. But we could also express this a little more elegantly. through recursion. So you see here, we're really just multiplying n with n minus 1 and applying factorial to that. What does that look like in code? In code, a step-by-step solution might look like defining a function called factorial and passing it a value of n. You start off with a result of 1, and then you utilize a for loop for I in range of n to 1. We are going to iterate by -1. And the result will be equal to the product of that value and the current result. And you repeat this until you retrieve the value that you need. A recursive approach has a few less lines of code. And we're not utilizing a loop here. We're not utilizing a for loop. We're simply utilizing a condition. And the function is self-referencing. So you define a single parameter, or let's say your base case here. If n is equal to 1, then we return n, because in this example, our base case is n equals 1. So we are going to return n multiplied by the output of this exact same function, but this time we're going to pass in n minus 1. And this is how you essentially achieve the behavior that occurs here. And so you have a much cleaner looking solution, a few less lines of code. You don't have to rely on built-in for loops, and this can come in handy in many cases, maybe primarily during the interview process when you're being given a challenge or a whiteboard problem to solve. You won't have to worry about stumbling over variables or elaborate explanations behind large and long for loops. Instead, you have the reduction of complexity to a very simple and repetitive concept. So I'm going to stop sharing this screen here, and we're going to switch over to VS Code. Does anyone have any questions so far? How do you all generally feel about recursion? I know a few of you have already demonstrated a knowledge of recursion in some of your challenges, at least with me. And so I'd like to get your thoughts right now. Anybody very comfortable with it? Anybody very turned off by it?
Not turned. Sorry.
You go.
So I was just going to say that for me, I have looked at YouTube videos like other people like trying to explain this, and I don't get it. Like, so if it can be explained in the most elementary way, that I would appreciate that.
Okay. Anyone else?
I feel like when I watch the problem get explained, I understand it. And I feel like when I go to do a new problem, my mind just gets all wrapped up and I'm just like, oh man, I need to go back to the drawing board and study.
Head on.
Yeah, like that simple fact, like that factorial one, it's like I see it and I get it. But I also seen other problems where you put like you call the recursive function before you add the result, and like it causes the stack to kind of go a completely different way. And so that right there kind of confuses me.
Mm-hmm.
Yep. I've used it like a decent bit, but I generally like to try and avoid using it. Just because like I do find it still to be confusing or like harder to put together, but I also don't like, it seems really inefficient that like, when you calculate 5 factorial, you're not just calculating 5 times 4 for one result. It's like you're doing the results many times over. It's like you're making the computer, calculate 30 things when you only needed to calculate 5 things.
Those are some very interesting thoughts. What about so I get the general consensus is that there's there are arguments to be made against maybe its efficiency, right? But I think once you really start to wrap your head around it, it's first off, it's good that you're already starting to make those arguments. You're already starting to formulate in your mind, the pros and cons between process of recursion versus, let's say, imperative or iterative solutions. So that's good. But the more familiar you become and the more comfortable you become with recursion, the more you may be able to see its benefits. And there's kind of this is kind of why I started the presentation the way I did, kind of talking about some of these more abstract or fundamental qualities to it. It's kind of like how it may be easy enough to learn, but a lot more difficult to master. And I definitely would still argue that it may not be something that you utilize often, but to know it and to be able to refer to it from time to time will definitely work in your favor. It's just another tool to have, and it will push you to think in ways that relying on loops and whatnot traditionally don't. It activates a kind of resourcefulness that you won't get through more imperative or iterative, straightforward problem-solving methods. But of course, that's more theoretical and advanced. Right now, we really are just concerned with understanding recursion at face value. So I do hope that this 5-step process is elegant or simple enough that you'll be able to understand it easily, Harry, and the rest of you. So let's dive right in. Let's use another example. We're going to write a recursive function that, given an input of n, sums all non-negative integers up to n. So whatever value we assign to n, this function will sum every integer between 0 and n. So an iterative solution may look like this. You're defining a function called sum. You're passing in a parameter of n. You're starting with a variable that you're going to eventually print out as a result. We're going to set it to our base case, 0. And then we're going to use a for loop. For I in range of n plus 1, the result will equal itself plus 1, and then you return that result. Similarly, a mathematical solution that you could just plug into a calculator would be n times n plus 1 divided by 2. And if we were to try some of these right now, let's see if I still have sum in here. Say the sum of 10 results in 55. And if we pull up a calculator, though I'm not sure you'll be able to see this. Let's take that same number, 10 times 11 divided by 2, we get the answer of 55. Now, what would this look like in recursion? Let's approach this utilizing that 5-step method that I mentioned earlier. So the first thing you want to do is you want to identify a starting point, and that's going to be your simplest possible input. Basically, what is my base case? The base case in this scenario would be that the sum of 0 equals 0. This is the simplest possible case because we're only dealing with non-negative integers. Step 2, let's start playing around with more complicated examples. We're collecting data, and so we want to be able to start extrapolating some information by comparing this data. So if we had an integer, an n value of 1, every non-negative integer between 1 and 0 sums up to 1. Let's go up to the next value, 2. 1 plus 2 equals 3. When we get to 3, we add 1 plus 2 to 3. Does anybody see a pattern so far?
Yes.
Would anyone like to try to take a stab at articulating the pattern?
The pattern is counting from 1 to 1.
It looks like your n values are incrementing, and if you add them all up, they equal the value. What is that? 10, 6, 3, 1, yes, 4, 7, and 10, right? So 4, 3, 2, 1, if you look at the bottom of them, they all add up to 10.
Mm-hmm.
So it seems like they are, I don't know. I mean, that's what I noticed. So I don't know.
What about the visuals? Would anyone like to take a stab at articulating the pattern through the visual, through this little triangle of blocks?
So the next block should be 20, I suppose. But it equals all the prior block sums before that.
Yes, definitely. Because we are following a pattern, we are really just expanding upon what already exists with each iteration. So you might notice that this block exists within this block, and the second block exists within this third block. In a sense, every time you iterate, you're just adding another row to the very bottom, the length of that row being the value of n. And so from comparing this data and finding patterns, finding conclusions, drawing conclusions, we can hypothesize and generalize the pattern. So on this left side, we have, let's say, n equals k. And prior to that, we had n equals k minus 1. So when we are summing up all the values between 0 and k, we always know that the step before it is 0 to k minus 1. And you can start writing these out as 1 plus 2 plus everything in between up to k minus 1. And if we try to then translate this into code, which is the final step, we get this. Basically, you have a function where you're defining sum, you're passing it in a value of n. If n equals 0, we return n. Otherwise, we add n to the sum. We're calling this function again recursively of that same value minus 1, because we know no matter what, there will be an n minus 1 or a k minus 1. And that will take us to the base case. So let's say we run this function, we go through the initial function and we hit a recursive case, which adds 5 to the result of calling out some function on the input of 4. N plus sum of n minus 1 will look like 5 plus sum of 4, which will look like 4 plus sum of 3, and so on and so on and so forth until we get to 1 plus sum of 0, our base case. Have I lost anyone yet?
So the question I always have here is like, on the final return statement, when you say n plus sum n minus 1, I know the answer will be different if you go return sum n minus 1 plus n. I mean, at least I'm assuming, so I feel like I've seen a similar problem and like the answer is different. And I'm kind of like, why is that?
Well, the reason that we are returning n plus sum of n minus 1 as opposed to n plus sum of n minus 1 plus n is this is the pattern that we were able to extrapolate from the data that we gathered. So once we collect all the additional cases beyond the first base case, we can see, for example, visually that every group of squares or every triangle is contained in the next one. So in a way, you can say that n minus 1 is, you could predict that n minus 1 exists. You could predict what the value of n minus 1 will be by subtracting n from the sum. And with that, you can write out the code that this is what you want to return. N plus the same function, but passing in n minus 1. Is that a little more clear, or is that still very confusing?
I'm still a little stumped, but I think I just with practice, hopefully pick it up better.
Right on. I did pull, oh, go on, sorry.
I was going to say I've definitely been confused by like a similar problem, and I don't know if this is like right at all, but like, is it because if you're returning and you have, here we're getting in and then calling the function, whereas if you call the function before you give it in, I imagine it's trying to calculate other things before it realizes what n is.
Well, when you actually call the function, what you're doing is you are providing the value of n. So we're providing, in this example, the value of n is 5. If we know that the value of n is 5, based on the function that we're writing out, there will be a case in which the value of n equals 5 minus 1. Because if we refer back to the original challenge, the original problem, we are summing all non-negative integers up to n. In a way, you could think about n minus 1 being the logical next step from n because of the goal of the challenge. So as such, it's not so much that it's calculating anything prior to you calling the function and passing in a value. The value you pass in is just the starting point, and the endpoint is the base case that you've defined. The simplest case, the base case, is essentially the case where the starting point and the base case are 1. You can't get any simpler than running this function on a value of 0, for example, or a value of 1. Because when you subtract a non-negative integer from 1, you reach 0. Does that help?
Can you then do recursion infinitely, as it happens with loops that are written in, like, can that happen?
Yes, that could definitely happen, but I would say that would happen if you're not writing out your recursive function correctly. Because you start with a base case, or I should say by starting with a base case, you're setting a destination, you're setting a goal. You want to reach that base case, and you don't want to go beyond that base case.
It kind of helped, but I think the confusing part is like in this case, like, will we return a different answer if we switch because like to me it doesn't make sense. Like if n is going to reach 0 or the base case at some point, why does it matter that we do the recursive call plus n or n plus the recursive call?
Because we are trying to sum all non-negative integers up to n. So n becomes the starting point. We have to add n to the value before n, and then the value before that, until we get to 0.
maybe it would help to see
So-
the stack, possibly how recursion stacks and then reconciles from the last case down.
I kind of have a quick question. If you scroll down to the problem there, or all the way down, down to where the recursion code is. Yeah, right there.
Mhm.
Why wouldn't it return 0? Would it just return 0 if you ran that code?
You can't run the code without passing in a value for n. So you would have to have a starting point. The only case in which it would return 0 is if you pass in a value of 0.
So can we see that then, like, let's say that you put 10 there,
Mhm.
like what's gonna happen? So essentially it's gonna be assuming it's hard, it's really hard to wrap my head around this, but I guess that would be an interesting thing to see what the code is doing. I'm trying to imagine, because I think because there's a minus, it's just gonna be removing one thing and removing one thing and until there's nothing.
Mhm. Until you reach n equals 0. So let's start with this. Let's start with defining this function so that we could call it and play around with it. So this is where the recursion is happening. When we're calling the exact same function, when we're having it call itself, and we're telling it what value, we're giving it a value that we know we'll want to give it. If n is the starting point and 0 is the base case, and we're dealing only with non-negative integers, in order to reach the base case from n, we have to subtract by 1. Otherwise, we would be missing or skipping over a non-negative integer. So let's see it in action. Somebody wanted to see 10, right? It returns the same value that we saw earlier. Now, how can we add some print statements to this so that we could see it happening live? Let's try this. If n equals 0, same thing. We're going to return 0. Else, maybe we want to print the current value of n. And yes, feel free to correct me if my Python syntax is wrong. I work in Ruby all day, so I may occasionally mix things up. Does this look good for our print statement?
I think that should work fine.
Okay,
How
cool.
come on the return you have to return 0 and not just n?
If you return n when you get to 0, okay, actually, how should I answer that? Because that is a very good question, because I guess if you're passing in 0 for n and you return n, you'd be returning 0. So
Yeah, I mean, it definitely worked and when you did it. So I know, I mean, I get it's got to definitely work.
Mhm.
It's just, I don't know.
I think that's what I was trying to ask as well.
All right, let's see it in action step by step first, and then let's revisit the possibility of returning n. So let's start with, let's see if our print statement works first off. It looks like it doesn't. It doesn't like my print statement. It does not like my string concatenation. And can anyone tell me why?
I think you might have to do like a plus equals or something like
Or,
that.
oh, actually, never mind.
There are two type of what's that called? data. So one is a string and one is an integer.
Right on. So let's convert that integer to a string because we really just want to see it in a print statement. Can anyone tell me what the method for converting integers to string is in Python?
You could just do an F string.
I could just do an F string. Am I using quotations or backticks or what?
Just quotations and then put the variable in squiggly brackets, curly brackets.
Like this?
Yeah, that looks good. Do you mind hitting command plus once?
Oh, yeah, sure.
Oh,
Okay.
yeah, there we go.
Okay, it looks like it's going bonkers on me. So let me retype this. And our last line should be returning n plus sum of n minus 1. Let's give this a shot. See n equals 1. We see n equals 2 during the first step. And then once it calls itself again, n equals 1 because it's returning n plus the same function, but with the previous integer passed in.
So it basically doesn't give it a chance to reach 0 to return 0, I guess.
Exactly, exactly. What we're really returning is the sum of this, of n, and the return of the same function. So because we're always returning n plus something, eventually at some point we're going to be returning n plus 0. So if we were to replace this line with n, let's see what happens. Let's see how it breaks. But before we do, let's also, I should actually define it as a different function. That's what I'm going to do. I'm going to call this sum, I don't know, sum2. Very creative, I know. And we are going to do the same thing, but we are going to return n this time. Would anyone like to predict how this will change our results?
I'm guessing it won't.
Okay, any other predictions?
I'm guessing there's a possibility that it won't know what to do with n minus n for the sum. And then because it doesn't have a value, you won't be able to return anything at all.
Okay, do you think it will error out then?
Possibly. But part of me also thinks I could see why it would work too. But that's the only reason why I would think that your base case needs to have an actual value.
Right on. All right, let's give it a shot. I'm gonna do sum2. Somebody name a number.
5.
5? Cool. Looks like it returned 15. So did it ever reach this point?
Yeah, I never had a chance.
What about when we get to n equals 1? Wouldn't it be that during that function, when we're calling sum2 and oh, actually, I noticed something. Let's redefine this function. And does anybody see what I did wrong?
Say that again, where?
Does anyone see what I did wrong defining
It
this
sh-
second function?
It should be return n plus sum 2.
Exactly.
And then
We did not see it break because it was calling the first function. So let's do this again. I'm going to do an else statement here. I'm going to do our print. And we are going to return not n plus sum of n minus 1, but n plus sum of 2. Or I should say sum 2 of n minus 1. And now let's give this another try. Wow, looks like it did the exact same thing. And so let's step through it. What is happening here? If we get to a point where we're passing in a value of 1, I would have thought that, and well, I guess it doesn't matter. It's irrelevant because once we get to a point where n equals 0, it's going to be returning 0. So I'm sorry, I already forgot who brought this up, but whoever brought it up, you're right. It's kind of irrelevant, really.
I see why it returns 0. I mean, why the return 0 works as well now, because it's just n plus 0 for the last recursive call to that function. So if n already has a number, 9 plus 0 is still 9.
Mm-hmm.
So that also helps, because I was just thinking about how like different problems would work if you return the whatever. Yeah.
Right. And ultimately, this only happens when we get to the very end, when 0 equals 0. So if this only ever happens when n equals 0. So regardless of whether we're returning 0 or returning n, it's going to be returning 0.
Is it just because of this particular problem? Like, if you wanted to do like the opposite with the recursive function, like count up,
Mm-hmm.
would that throw an error then? Like, because now, I guess the last number, I don't know. Maybe I feel I just lost my train of thought.
Okay, well, let's step through it. You said you wanted to see a case where we're counting up. In the situation where we're summing all non-negative integers counting up, let's first try to write that out in English. What would that be? So let's say maybe the challenge becomes, given an input m, sums all non-negative integers up to m. But that doesn't seem right. That's exactly still giving us the same thing. So you say you want to be counting up, right? Are you talking about the implementation? Are we changing the implementation, or are we changing the original?
No, so I think what I was thinking about a different problem. It didn't sum it. It just like printed out the numbers in like descending order, like 5, 4, 3, 2, 1. And then the other one was it printed the numbers 1, 2, 3, 4, 5. So basically going from descending to ascending. And I thought if we changed the base case from 0 to n, it would affect it.
The thing is, though, you don't really change the base case. The base case is what you find based on the problem that you're given. So if you change the base case, you're changing the problem. You're changing the ask.
Okay, yeah, that makes sense. Yeah.
All right. I think how does everybody feel right now? Right on. Right on. All right, let's talk about challenges. So the rest of the day, we're going to be doing a few challenges. The first is pretty simple. It's recursion with loops, I believe. I think you're going to be trying to replicate the behavior of a for loop, but through recursion. Let me share this other window. Let me know if that's still too small. And no, that's not what is it? Okay. The first challenge is going to be the recursive loop. While looping is great, it's not the only way to iterate. In fact, looping is frowned upon in functional programming. All right, this talks about Haskell a bit. But basically, you're going to be writing a function that takes an integer. That function should print all the integers from 0 to that integer. And then you repeat it, but this time counting down to 0. Let's see. Let's have you all take a stab at this alone. And for the next challenge, I'll have you work in pairs, because the next challenge after this one, you'll be revisiting some of the problems that you've solved already, but utilizing recursion. So you'll be going back to factorial, palindrome, 99 bottles, and Roman numerals. So let's knock out the first one pretty quick, so we could have more time to do the more challenging one. Let's say, does this still apply? Yeah, let's take a break. Let's have you all come back at 6:30. We shouldn't need more than 15 minutes to solve the first challenge, at which point we'll start reviewing. We'll take another break, and then we'll spend the rest of the evening pairing up and working on the final challenges. How does that sound? Right on. All right. Feel free to take a break and jump right into challenge 1 when you get back.